Okay, so we're starting to prove this theorem that says that a norm space X is complete if and only if every absolutely convergent series converges. And we're starting to prove the forward direction, so we assumed that X is complete. We have to show every absolutely convergent series converges, so we start with a series, summation from 1 to infinity of X of n, that converges absolutely, and then we have to show that the series converges. Now, since we've assumed that the space is complete, to show the series converges, it's enough to show, so let's say it suffices to show that the series is Cauchy. How are we going to do this? Well, our other assumption is that the series converges absolutely, so the sum of the norms of the X of n's is finite. It converges in the real line, and therefore it's Cauchy as a series of real numbers. We'll use that. To show that the series is Cauchy, I have to start with an arbitrary epsilon, so let epsilon be greater than 0. Now we'll use the fact that the series of norms converges. Since the series summation from 1 to infinity norm of X of n converges, it is Cauchy. So we can choose an n sub 0 such that the sum as I goes from n to k of the norm of X of I is less than epsilon for all k greater than or equal to n greater than or equal to n sub 0. Note that in the real line, I don't have to bother putting absolute values bars around this sum because it's a sum of non-negative terms. And now from this, we'll quickly see that the original series is also Cauchy. I'll leave this stuff here for a minute. So I can say then, for k greater than or equal to n greater than or equal to n sub 0, norm of the sum as I goes from n to k of X of I, well, that's less than or equal to the sum of the norms. The sum as I goes from n to k of the norm of X of I. I've just applied the triangle inequality for the norms. Let me put that in parentheses, triangle inequality. The triangle inequality for the norm is just expressed in terms of two vectors. The norm of the sum is less than or equal to the sum of the norms, but by induction it works equally well for any finite sum. And now, what I see here is exactly what occurs on the left-hand side of this inequality, so I can continue and say this is less than epsilon. Now let me erase this. And so I'll verify the Cauchy condition for the series. Therefore, the series is Cauchy and therefore converges because we've assumed the space is complete. That finishes that half of the proof.